TTL Computer 2. Today we'll be taking a look at the design and the first part of our build for TTL Computer 2's permanent power supply. And we have to deal with some particular current issues in our power supply design. And to refresh yourself on the details of that, you could review video number 39, which is the backplane update. Okay, so we're taking a look at the schematic for the current control circuit for the power supply. So let's take a look at what we have here. So what we're building is basically a slow start power supply where the when the power supply is turned on, it's going to ramp up the current to the computer in this case slowly. So it's gonna power up at a time at only 1 amp, and then after a predetermined period of time, it will switch to full power. It will be available to TTL Computer 2. So that's what we're doing. And we'll just look at some of the components here first. So the heart of this circuit is the MOSFET, which is a power transistor. And we'll come back to that to talk about that a bit. We have a 5 ohm 10 watt resistor, and that's going to be our main power resistor that will initially limit the current to 1 amp that's going to TTL Computer 2. Then we have a 10K resistor here. That's a pull-up resistor for the MOSFET transistor. We have a current limiting resistor here for the gate of the MOSFET. And then I'm going to be using a small microcontroller, a small PIC microcontroller that's going to take care of the timing for the circuit as to how long it's going to stay in the low power state before it switches to the high power state. And then we have a fuse, a 4 amp fuse that will limit the current that TTL Computer can draw from the power supply. And then we also have just the power indicator LED, a 2K ohm resistor limiting the current to the LED. And the LED is wired, in parallel with the output of the power control circuit. So this way, if the fuse does blow because of an overcurrent situation from the computer, the the on indicator LED will be extinguished. So it will show us that the fuse has been blown. So, the main power circuit is potentially is still operational. Okay, so that's our basic design. Now, let's talk about this MOSFET for a little bit. This is the first time I've actually built anything with a MOSFET, and I think that stands for metal oxide semiconductor field effect transistor, is what I believe that stands for. And these have a bit more technical requirements to operate than does a standard bipolar transistor. A PNP or an NPN transistor has more details that you need to care for in the operation of these MOSFETs. But one of the key things here is that all right, so there's three leads. There's a source lead, there's a drain lead, and there's a gate lead to the transistor. And in a MOSFET, the gate acts as a capacitor. And since this is a P channel, when voltage is applied, positive voltage is applied to the gate, the transistor is off. And since the gate acts as a capacitor, that can build up a reasonably large charge on it. So when the PIC decides to turn on the full power, it will drive the gate line low. And we need to limit the current that's coming out of this MOSFET gate back to ground. And we need, just like we're doing this whole thing to to care for capacitor, charging, capacitor charging, we have to care for the capacitor discharge here because we need to limit that current so that you know, uh, we do not sink more current into the microcontroller than it can handle. And this microcontroller can handle 25 milliamps, and that's how we come up with the 220 ohm resistor here. Is it's limiting this current to just under 25 milliamps. So if you're using a MOSFET, that's one of the things you need to really care for and calculate that resistor value. And that's a real oversimplification of the MOSFETs. There's a lot more details uh, that need to be cared for when you use them. And the P-channel MOSFET is a little bit easier to use and has a lower hurdle for requirements than the N-channel does. Okay, so that's a lot of detail on the MOSFET. That's probably the most interesting thing in here. So, all right, so we have +5 coming in. So this pull-up resistor is going to keep the MOSFET transistor off. So that means no current can flow this way. So that means the full 5 volt is going to come through the 5 ohm resistor, right? And through the fuse, and that's going to come to TTL computer 2, right? So it's the 5 volts limited to 1 amp because of the 5 ohm power resistor that we have there. The microcontroller, once it's powered up, it's going to start its timing, and I have it set so after 200 milliseconds, it will bring the MOSFET gate low, and that will discharge the gate through the 220 ohm resistor into the microcontroller. That will turn on the MOSFET, and that means that there's going to be a very low path for the power to go through the MOSFET and is going to bypass the 5 ohm resistor. So essentially the full power, the full 5 volts will come through the MOSFET, bypass the resistor, through the fuse, and TTL computer 2 will get the full current and voltage to the computer. All right, so that's our schematic and what we'll be building. Now, what's not shown here is that we're going to have a separate 5 volt, 10 amp power module that will be feeding this current control circuit. But we won't be looking at that today. We'll look at that in the second part of our build. Okay, so that's what we're building. And as I said, I want to breadboard this first. So what I've done is I've breadboarded the main circuit without the PIC microcontroller here. So you can see that there's a resistor network here. We have the power MOSFET is here. And then I have a manual push button that will turn on the transistor, turn on the MOSFET, and make the circuit go in full power. But right now it's in the low power state, and we can see here that there's 0.24 amps is what's being drawn in the low power state. And then here I'm pressing the button in the high power state. So this activates the MOSFET, which bypasses the current limiting transistor, and we can see that the power essentially doubled to 0.45 amps. So that's our solution, breadboarded and validated the operation using a manual switch. Okay, and then all right now, so I've programmed the PIC microcontroller, and that's installed on our breadboard. And now we have that is hooked up and is controlling the switching of the MOSFET. Now we have essentially a shunt resistor here, and we're hooking that up to the oscilloscope, and we measure the voltage across that shunt resistor. And that gives us a way to indirectly measure the current that's being drawn through the circuit. Okay, so that's now PIC's programmed and installed and is controlling the MOSFET. And now we can take a look at that on our oscilloscope. And here we see that. So here, the whole circuit is off. At this point, the circuit powers up and comes up going through the current limiting resistor. And here the PIC microcontroller starts its timing. Here's 100, here's 200 milliseconds. It enables turns on the MOSFET transistor, again, which bypasses the current limiting resistor, and we go to full power. So there's that stair step, right? We're essentially like at 50% power, and then 100% power will be delivered to TTL computer 2. Okay. Now, this is just a sketch out of the component layout for our perf board that I'm going to be using, right? We have our, plus coming in. Here's our power current limiting resistor, our MOSFET. Here's the PIC. Here's a 4-amp fuse holder. And then I just have the LED, the power LED is just indicated here. So that's what we'll be building on our perf board. And here's the start of that. So you see our power resistor is pretty large here. This is a 10 watt. We probably could have gotten reduced this quite a bit, especially since the power is in the high power state, only for 200 milliseconds. So, but that's what I was able to purchase. Here's the MOSFET. Here is the 10K pull-up resistor to the MOSFET. Here's the 220 ohm resistor that's limiting the current to the PIC, and here's where our PIC will go. All right, and this is our completed control circuit on the perf board, and that's all ready to go now. And I'm going to just hook that up and test the built circuit on our scope again. And we can see here that we have the same behavior that we saw in our breadboard version, right? The circuit is powered up. It comes up in the 50% power level after the 200 milliseconds, right? The PIC turns on the MOSFET, which bypasses the power transistor and outputs our full power to TTL computer 2. Okay, so that is the first part of our build, and our control circuit is all done and tested. And the second part of our build will start to add that along with our power module into an enclosure, and we'll get that all together and wired up, and we'll look at that in detail and test out the final product in our next video. So until next time, thanks for watching.